Okay, I hope to today give you a pretty good overview of basically the Shack-Hartman wavefront sensor technology and a lot of the applications that I've worked on particularly, and perhaps even a little bit of the history behind some of it. So that's kind of the organization of my talk. I'll go into a little bit of detail on how to design wavefront sensors for a particular application and some of its things like the precision, how do you measure precision and accuracy and define some of these things, and then I'll show you some of the applications as well. So this is sort of a laser weapon right here. This is actually where we started off developing some of this technologies, working actually on high energy laser weapons for defense kind of applications. And it kind of devolved into, you know, how can we sense light better, and that's sort of what the basis is. So the thing that I'm primarily interested in measuring is the phase. And phase is very often measured with an interferometer. Interferometer is a very powerful, very well developed. There's still many new flavors of interferometers being developed. It has a lot of advantages. It's got very high resolution. There's commercial systems for measuring optics available. But in some situations, particularly a laboratory kind of thing, it has some problems with robustness. Depending on how you implement it, it may be difficult because of vibration. So there's other techniques, and the other technique that is one of my favorites is the Shack-Hartman sensor. And so the Shack-Hartman sensor is a very simple kind of optical concept. It's just a lenslet array in front of a detector. And the lenslet array dissects the incoming light, the wavefront of that incoming light, up into a series of small focal spots. And the position of those focal spots has information of the direction the light is traveling at each point. And you know, I joke the only physics behind the Shack-Hartman sensor is that light travels in a straight line. It's just connect the dot from the center of the lenslet to where you found that focal spot, and really you've got the main information. But there's a lot of other advantages. It's completely a passive sensor. You don't need an active reference beam. You may be able to use a reference to record some really high quality beam going through an optical system, but that can just be pre-recorded. You don't have to have that be there present when you actually make the measurement. It can be designed to have a very large dynamic range or be very, very sensitive. And just by scaling the focal length of the lenslet or the size of the lenslets, you can vary that over an extremely large range of for different kinds of applications. It can be made to be, like say, high sensitive. They're fairly insensitive to noise sorts of effects from the detectors, very often used in astronomy for that reason in many cases. But in measurement applications, it turns out that's a very weak effect on the phase. So you don't have to have a phase unwrapping like you might with an interferometer. However, you have to have a wavefront reconstruction, because what we measure is the gradients, it measures the slopes. We don't really measure the wavefront itself directly, and I'll show you a couple different schemes that are used for doing that. It's very simple, compact. Really, it's no bigger than the camera itself. The lenslet array fits a few millimeters in front of the detector typically, and so that leads to a little bit lower cost instrument. Although, as I found in forming a company, you have to pay all those employees that are writing all this software, and so somewhere in the way you have to charge for this at some point too. So. It also allows you a differential measurement. You can make a measurement through an optical system, record that as your reference, and then look for small perturbations or changes to that. And that's very useful in some kinds of measurement applications. So I just spent a couple minutes going over the history. I like to understand the context of where the thing that I'm working on fits in with the rest of the technology and rest of the science. The Shack-Hartman sensor comes from Roland Shack and Johannes Hartmann. And Hartmann, his first measurements, he was tasked with measuring and improving the optical quality of this large refractor telescope back around 1900. And so he came up with this idea of putting a plate, a pattern of holes in front of it, and then essentially before and after the focus with pieces of graph paper, they just marked off where each one of those pieces went. They measured the distance with the ruler, and they essentially did a ray trace through focus. And from that, they were able to predict back what the aberrations of that lens must have been. And then they went back to the optician who, by hand, ground out those aberrations. And there used to be opticians who were really good at that. And I think it's a kind of a dying art these days. But, and they was able to actually then measure it afterwards and show that he improved the performance. And in fact, you know, it went from being a non-useful instrument to being a very useful instrument. And that actually became kind of a standard practice. People over the years changed it to sort of a square grid. they've applied computer techniques. In fact, Daniel Marquardt in his book on optical shop testing described it as one of the sort of standard techniques for testing optics and for testing mirrors and telescopes and those kinds of things. And so, and that was kind of the status quo until about 1971, when Ben Platt, who was a grad student at Roland Shack in Arizona, was tasked with developing some phase sensors, and I think it was actually funded by the DoD at that time, by the Air Force. Ben came up with they came up with the concept of a Shack-Hartman sensor, and the first publication is a little bitty short abstract, a paragraph and a half or something is the first publication on it. And it's really, Roland Shack really did two things, is he moved the measurement plane away from the focus, he moved it up to the pupil, so that he's measuring the aberrations over the pupil. And then he created the separation not by a series of holes, but by using a lenslet now, which measured over the whole area. And so those were really his two key advantages. What Ben Platt did is we made a gizmo to make these lenslets. No one had ever made a lenslet before. And so, and he took a ball bearing and with a step and repeat process, pushed it into a piece of plastic repeatedly, and then he put a little epoxy in that, and he made a mold that when he peeled this out, he had a little lenslet. So. And it was the first ones were kind of by hand, and they were a little too crummy to be useful, but then over time he automated that a little bit, and he actually, AOA today still makes them with that same kind of process. Yeah. Yeah. Now, I say that the molds are diamond turned and all that kind of stuff. But it's still molded. Yeah, no, sorry, didn't mean to imply that. So and he actually made pretty good lenslets, and interesting enough, it was really Ben Platt's employees from Ben Platt's company that were working with me that led us to the development of the first Shack-Hartman sensor at Sandia. So it's kind of funny how there's connections all the way across here. So in the 70s, the Shack-Hartman sensor was used primarily, I think, in high energy lasers and adaptive optics. It's beam control, beam cleanup. They were a few channels, but there were big programs that the military was developed for trying to steer and control laser beams. And one of the problems they had is if you got a laser powerful enough to burn holes in a missile 100 miles away, it was also powerful enough to burn holes in your mirror and your optical train and to heat those things up and distort them. So you needed to do something just to fix the beam itself from its own problems. And so some of the early systems were, like there was shearing interferometer systems, there were scanning sensors, but some of the early systems, some of the early Shack-Hartman sensors they were considered actually very complicated because they were sort of individual lenslets with some sort of quad detector behind it. Each detector had to be individually aligned to that lenslet. And so by the time you had even 16 channels, you had a very complicated system with lots of optimization. They were considered, yeah, you could do this, but it's very expensive, very complicated. It's just feasibility is limited on that. And so when they started trying to make lenslet arrays, and there's another way to make a lenslet array. You can take a set of cylindrical lenses and cross it with another pair of cylindrical lenses 90 degrees, and now you've got a pretty decent lenslet array, actually. And in about 87, 89, I think, people started using those in Germany, a lenslet array like that, to look at the eye, actually. It was the first time people looked at the eye measuring it. So in the 80s, the military advanced that, and they started building a full adaptive optics systems driven by a Shack-Hartman to look at astronomical objects. The military is interested in satellites, of course, and the astronomical community really lagged that. That was all very highly classified at the time. And then right around 1989, 1990, the astronomical community was coming to that on their own. They had completely independently developed it. And at that time, the military decided to make their efforts public so that partly they could get a little credit for it. It was going to be public anyway, so there was no real reason for them to keep that secret anymore. And so there is a big site there near Albuquerque, the Starfire Optical Range. There's a 3.5 meter telescope there now where for something like 30 years they've been doing adaptive optics. And and that has all, of course, developed as the technology came along significantly throughout the 1990s, and pretty much every large telescope now has some form of adaptive optics system, usually with a guide star system on it as well. So these systems really can improve. Now, I first came into this tasked with measuring the beam quality of our high energy lasers we were trying to build, and measuring the quality of the medium of the laser medium of the laser we're trying to make. And our lasers were actually pumped directly by a nuclear reactor at Sandia. And so we needed something that could respond. These were pulsed reactors. The reactor pulse lasted about 12 milliseconds. And in that time, the optical distortion would range from starting at the beginning of the pulse to being essentially perfect over infinity to being a 70 millimeter effective lens during that 12 milliseconds. So that was a pretty fast change in the optical aberration that was taking place. And so we needed a way to measure that. And in discussion with Stuart McKechnie, one of Ben Platt's employees, we came up with this idea of taking a little group of cylindrical lenses with a line scan camera that we could run at 20 kilohertz. And we only measured it in one dimension, but it was a wall pump system, and really the primary aberration was in one dimension. And so that matched very well with the problem that we had at hand. At the time, our data acquisition was a KMAC crate that was considered an extremely high-speed computer. It ran at 1 megahertz, but it was a 12-bit channel. We had room for lots of data acquisition. And what was amazing was when we analyzed the data with that, it was super good data. It was lambda over 100 data and had hundreds of waves of dynamic range. And so it was like, that caught my eye at the time, was going, well, that's kind of unusual to have an instrument that has that much dynamic range yet can also make that accurate instruments. And so that sparked my thinking that this might have some further applications. The lenslet array was still kind of crude with a bunch of individual little lenslets that I pieced together with tweezers. So, and about the same time, I was working on an internal development project to develop the micro-optics technology, which is basically using computer technology to fabricate structures in fused silica using etching, photolithography, those kinds of techniques. And I'll give you a few more details on that as we go. And so this second one is a 40-element micro-optic sensor. I think there might be, yeah, this is a profilometry across that lenslet. And so you can see we were able to make the little lenslets. Our first prototypes were done with a binary process. We used multiple masks to sort of slowly build up the structure from different levels of etching. And the neat thing about micro-optics is you don't have to make regular structures. They can be, you can add tilt to each of the lenslet. And so each one of these lenslets has got a different center so that the lenslets approximate an area around shape, but the spot pattern they create is a square grid. So it's kind of typical pupils are round and typical detectors are kind of square. So that was our thought here. And this is just a course demonstration. We thought this was a kind of a neat picture, as we chose this as our company logo when we eventually formed the company. But you can also divvy it up into a whole bunch of little squares and then sort of multiplex it. So if you can see there's sort of patterns here which divvy us up into quadrants and compare the individual quadrants. And then across each one of those, there were comparing quadrants. This is which is a phase comparator, which is for comparing the phase of different segments of a 64 segmented mirror. So anyway, so there's things that you can do with micro-optics which you couldn't do with any kind of conventional fabrication. And this technology has only gotten better from what it's quite amazing what you can do this. And I think there's a lot of things which we may even underutilize this. There's some power here which I think could be utilized even more. So let me go into wavefront sensing a little bit more in a little bit more detail. So again, the thing that we primarily measure is the focal spot position. We do that usually by looking at a group of pixels assigned to that lenslet and doing a centroid calculation of some sort. You'll put some reference beam in, some really high quality beam. That could be a collimated beam, or it could just be a spherical wave. And the advantage of the spherical wave, it just comes from a point source, which is very easy to generate. And then you subtract the reference from it, you divide by the focal length, and now you have the slope of that particular beam. Then that just is the gradient equation that you have for the slopes in 2 dimensions, and you just can be the phase by integrating that. Oops. The key is good lenslet arrays, and I think someone asked me if we use a high quality lenslet array, and there's an important parameter of the lenslet array. It's not so much the profile of this that's important. What's important is not to have any light leak between the edges. If you have any light that leaks through the corners, then what happens, that light, especially if it's coherent, can interfere with the focal spot. And then as that focal spot moves around, you get very different performance. And so that's one of the keys to having a really good Shack-Hartman sensor, is to have a lenslet array that is 100% fill factor. And that's one advantage of this micro-optics. This is an early one showing this discrete process. And these look like they're there's a gap here, but this is just a shadow. I had to put the light at a real shallow angle to be able to see it. These ones are 100% fill factor as well, and here you can see blown up some of the more recent ones, and you can see that they really truly fill all the way to the corners of these. And you can make these actually very accurately. We make them now with the grayscale process. We write a mask that's sensitive to E-beam light, and we create the pattern that we want in that. That's just a varying optical density pattern. You put photoresist onto a fused silica substrate. You expose through that mask with UV. Typically with contactor, you could use pretty much any method. And then you etch that with you can use a reactive ion etching, but we actually just raise the pressure and use a plasma etch because it's isotropic and it smooths out any little bitty irregularities. And for an optic, we like those things to be a little bit smoother. We don't really want those really sharp edges. And so that and you etch until all the photoresist is gone, and then that transfers that pattern into the fused silicon. You know, with a very high quality fused silica lenslet, it's very robust, and it's got features that you were able to design into it. This is a little bit about the calibration step. The photoresist is a little nonlinear, so you just put a test strip on it, sort of like you, all of you guys are too young to remember doing photography in the darkroom, but that's what you used to do in the darkroom. So, but you build a test strip, and then you've got this curve that you then fit to the transmittance function, and by the time you linearize it, you get extremely linear results out of it. So it's very predictable how you're able to do that. Anyway, so that's a little bit of an aside, but it's an interesting piece of technology that I think you could keep in your toolkit, if you will. The first step in a Shack-Hartman sensor is to measure where those spots hit. Where do they fall? And they're falling on a group of pixels. Typically, this one is a group that is 7 by 7, and this one is 25 by 25. So those are sort of the typical ranges of the extremes of how many pixels you would assign across a lenslet. But we really want that information at much less than 1 pixel resolution. We want the information to be a small fraction of that. And we've got quite a bit of information about this focal spot. There's some things here which confuse us, which is like these side lobes you can see. Those, the exact arrangement of those is going to depend a little bit on the side lobes of the one next to it and how close they are together. So you really want to filter those out. But there's some really simple ways to do that. You just threshold it. You just set a threshold, 10 or 12% typically. And then you look at primarily just the center region, use a very conventional centroiding algorithm. The key though is that threshold. Make sure that you apply some kind of threshold. And the results depend strongly on the threshold. Here's an example of a couple different thresholds that I'm showing here. This threshold here is a 12% threshold. We just found the brightest pixel, and then we set the threshold at 12% of that. And those are the spots you keep here. There's another one, we call it area threshold, which is a little more sophisticated. What we do is we find the location between these side lobes, and we essentially draw a box at the minimum place around there, and we keep everything inside that box. And so we are excluding this now based on area rather than on a height. And this is the one we found actually to be the most accurate algorithm. So, and sort of in real life, of course, you've got noise. That was a simulated image. But in real life, these things are not quite as distinct, and they're a little harder to find, but they still could be found. So, the next step is, of course, once you've got centroids, now you have to calculate the gradients. You do that generally with a reference file. And there's a number of ways to create reference files. You can just, typically I'll take the output of a single mode fiber and I'll collimate it with a good quality lens. And if you use sort of a 0.5 millimeter focal length lens, the little region over the center that's covered by the lenslet that you're actually sampling is maybe only a centimeter out of your 2-inch lens or something. So if your lens is a λ/4 lens, that little piece in the middle can be easily λ/100. So that's a very simple technique for doing that. And then you can use conventional things like a shear plate in order to set the collimation. Actually, what I do more recently is I take the lens out, and I just look at the bare fiber, and now I've got a spherical wave who's got 0.5 meter, or maybe I'll set it further back, a meter radius of curvature. And there's no optics in between. I just have a single point source. Now there is possibly air in between, and that air, any little turbulence in the air will give me a bias in that. But I just put a fan next to it, stir up the air, and then average for 1,000 frames or something. And then by the time I've averaged for those 1,000 frames, I have a very good estimate of where the center of those focal spots is. So, and as you'll see actually in some details, it turns out that because of the pixelization, there's actually a systematic error as the spot moves back and forth. And so if I'm moving that all around randomly and averaging, I actually average out those systematic errors. I actually get a more accurate measure doing it that way than I do just even if I try to create a perfect optic. So, and then, so the slopes are just subtract the centroids from the reference. I sometimes put the magnification of the optical system in there just because it's very useful to be able to put telescopes in front of this and either blow the beam up or blow it down, whichever thing you need to do. So, the other step is the reconstruction step. There's sort of two flavors to reconstruction. One is called the zonal, which is a zone by zone or a point by point kind of integration. It's really just a direct integration of this gradient equation. We've got the gradient of the wavefront is these slopes of the wavefront, but that is now what we measure. We measure these slopes. And so the other approach is what's called the modal. I'm going to fit those to modes. Zernike polynomials are the most popular, if you will, although there's many different flavors of those. There's some advantage to using orthogonal polynomials, but it's easy to convert to those orthogonals from other polynomials, and really the least squares fit is the thing that gives you the power of fitting. And you can see the difference between one case we have smooth surfaces, and the other case you can see the details of what's going on at some high spatial frequency level. And so in reality, I actually find it's almost always useful to do both. It's only another second computation in the computer usually for these, if that. And so subtracting them sometimes gives you some really interesting information. The zonal reconstruction, this is a method that I favor. It's based on a Southwell method. And basically you predict the phase at some central point from 4 different directions, and then you create an average of that, and then you go through and you do an iterative calculation. Typically 100 to 1,000 iterations. This whole process for a 70 by 70 grid takes 3 milliseconds, so all the way to iteration. So it's not a very, very time-consuming calculation. Computers are very fast these days. The other one is the modal calculation, where you represent your wavefront in modes, but we don't measure the wavefront, we measure the derivative of the wavefront. So we take an analytic derivative of our basis functions and write that in terms of 2 different derivatives, and then we fit those both together with the measured slopes. And so, and again, you can do these very fast. This turns out to take longer than the other way. And it's just because you've got all these polynomials that you have to evaluate each one at every point in your field twice. And so it's a little more time consuming, but still it's a second or something for a 20th order polynomial. It's not like it's very long. So, okay, so let me turn now to sort of the principles of design. So there's sort of 2 different flavors of Shack-Hartman sensor. There's one which is used for driving a deformable mirror, and it's very often used in astronomy or some form of adaptive optics. And in that case, you've got some corrective element that's actually in your optical path. And so your real goal there is to drive the error to 0, and you're counting on your mirror to be able to do that. And so really it's the mirror that has to have the dynamic range in that case. It's not necessarily the sensor. You have to have a certain amount to be able to capture it, especially if you're looking through, say, a turbulent atmosphere. On the other hand, there's a measurement approach where really I'm trying to measure what's there. I'm not going to correct anything. I just want to measure it. And so this might be a case where I'm measuring the eye or a silicon wafer or a missile seeker window or something like that. And so in those kind of cases, I need a large dynamic range. It needs to be very linear over the entire dynamic range. The accuracy of the sensor is the important part. And so these 2 sensors they may be both Shack-Hartman sensors, but they're driven by different requirements, and you end up with different kinds of goals. And so, I mean, the adaptive optics also speed is really important. Whereas if you're doing a measurement, you post-process usually, so you don't really care so much about the speed. So those are the 2 flavors. Now those lead to different conclusions about your lenslet array design. For your adaptive optics, you might really want to minimize the total number of lenslets because you're going to have to calculate these fast. You want to do this, maybe at a couple kilohertz in order to be able to have your measurement bandwidth be a factor of 10 higher than your control bandwidth. You want to focus all of the light that you can onto as few pixels as possible because you're looking at very dim objects when doing astronomy, for instance. And so you might want a long focal length lens in this case to maximize the sensitivity. Really, you don't care about dynamic range. What you care about is the final accuracy of and really it's ultimately the reference file that determines that. And you can, because you don't really care about that, the linearity and the accuracy over a large range, you can do things like put an optic in between the lenslet and the camera if that is useful to you in your optical design. Whereas in a measurement system, really you want that to be high resolution. The accuracy turns out to be strongly influenced by how many pixels you have underneath that focal spot. As I think I was explaining to some of you, an optimum seems to be around 50 to 60 pixels underneath the focal spot. You want to have significant dynamic range, which leads you to shorter focal length lenses. And you'll design your system to sort of balance those parameters, your accuracy and dynamic range that you need. And you might want to be careful about optics in between the lenslet array and the CCD or the detector, because those will introduce nonlinearities as a function of incident angle. And it's just really complicated to compensate for. So this is one approach that I use for designing lenslets. I define a lenslet Fresnel number, which is just the diameter of the lenslet squared divided by f lambda, and this is a dimensionless number. Typical numbers, this is a lenslet, a Fresnel number of 4 for this particular one. And another way to look at this Fresnel number is it's the ratio of the diameter of the lenslet divided by the size focal spot it creates. So this lenslet, and it's a little bit of a mixed nomenclature here because D is the full diameter but rho is the radius. So it's a little bit mixed in this case. But nevertheless, the focal spot here fills about half of the linear dimension in either case for a Fresnel number of 4. A useful range of these is sort of 4 to 8 to 10 is a useful range for lenslet arrays. So if you make them much higher than that, now you end up with very small focal spots that don't cover many pixels, and it's hard to get very good accuracy. You got huge amounts of dynamic range, but not very good accuracy. If you make them bigger than this, you don't have very much dynamic range, and now especially if it's coherent, these side lobes start to interfere with each other, and you start having problems in that case. So somewhere between 4 and 10 is a pretty good range. Now as cameras have gotten better and you've gotten finer and finer pixels, then now I can sample this. This is a 14 by 14 sample. If I've got 25 across there, then now I'm getting a very good sample of that focal spot, which does actually allow me to go to a higher Fresnel number in that case. And so the advanced camera technology is actually helping with this as well. So from that Fresnel number, you can calculate the focal spot size. In terms of that, you can estimate the maximum dynamic range. That's where the edge of this spot just touches the edge of the region underneath it. Now, we can do all kinds of tracking to track these everywhere, but you need, this is sort of the lenslet dynamic range, if you will. That's the basic parameter of how the lenslet array works, and that's relative to the system. And in terms of that, you can actually write the maximum, in terms of waves, the maximum wavefront that you can express for any given sensor in terms of the number of lenslets across the sensor, the Fresnel number, divided by 4 over n is the order of an aberration that you're interested in. So if you want to figure out what the dynamic range is for spherical aberration, n would be 4. It's a 4th order aberration. So I mean that's another way to estimate it. So this gives you some parameters and some design approaches that you can use to design a wavefront sensor to match a particular application. You have a certain accuracy requirement, a certain dynamic range requirement. Well, what kind of lenslet do I need to use? And usually I start with the camera and then work out these parameters, and then I'll try different models of cameras and look for optimal kinds of approaches. And so, this is kind of the design space, if you will, of that. It's kind of constraint driven. That curve of the constant Fresnel number is this curve here. Everything needs to be below that. This is focal length here and lenslet diameter here. There's some practical limit. I can't get the lenslet any closer to about 2 millimeters from the detector, just mechanically. There's some limits. I need at least a certain number of lenslets on one end, and I need a certain number of pixels across the lenslet on the other end. So there's limits on the diameter both ways. If I've got a certain dynamic range limit, then that translates to a curve here. And usually you end up picking a design that's on one of the corners. There's a optimal design theory that says the design will be at one of these intersections. So that's a typical places. And usually it's kind of, for this particular one, I think it was this point that we picked, this intersection with where we ran into the dynamic range. So, in terms of the precision and accuracy, I alluded to this a little bit. So it turns out there's a big gap between the precision and the accuracy of a Shack-Hartman sensor. The precision is just how well do I measure the same thing over and over and over again. And so that's really driven primarily by camera noise or some other environmental noise. And you can do a centroid estimate just by looking at the position of those centroids, looking at all of them and measuring a large measurement set, 100 or 1,000 frames or something. You can estimate the wavefront precision from that centroid estimation error just by dividing by the focal length. And now this is in the right terms for those to be slopes or gradients. And the wavefront across the aperture is just multiplied by that lenslet diameter. So this is a good number to characterize a sort of accuracy of a wavefront sensor altogether. There is a thing called a reconstructor factor, and the reconstructor depends. The zonal is a little noisier than the modal reconstructor, just because it's a point-by-point integration instead of fitting everything to a smooth surface. And so sometimes it's useful to consider those as well. If you look at this pixelization error, this is an experiment where we just vary the input tilt and over a 2.5 milliradian sort of range. And then we measured what we got with the wavefront sensor. And I'm plotting actually both X and Y measurements that we got. And the thing is, you notice is that the X, I moved this in the X direction, that if you see it here, there's a strong cyclic term that is apparent, and then it becomes even more apparent as you get out to the larger edges. And the period of this is exactly as the spot moves 1 pixel on the CCD array. So that's actually a systematic error that's a fundamental property of that whole centroiding operation. And it isn't as apparent in the Y, because in the Y, we're not really systematically moving across those. It's just sort of, some random variations that we're getting. So when I define the dynamic range of this, or the accuracy of this system, I'm going to say, if this is my dynamic range, I'm going to measure those all the way out to the edge of the dynamic range. I'm going to pick the maximum point. And I'm going to say, that sensor always does better than that value. However, for something that I really want to measure well, it may actually be almost a factor of 10 or 5 to 10 better in the sweet spot, somewhere if I'm moving a very small amount. So very small aberrations actually can do really, really well. And there's some experiments we've done where we've taken advantage of that. If you look at the accuracy of the total wavefront sensor, here's a case where I just took a very basic sensor. This is a 0.5 nanometer RMS that I got in I haven't moved anything, it's sitting in exactly the same position. And so it's very good precision, very good repeatability. However, if I compare that to my accuracy experiment, where I'm really putting in some known amounts of tilt, then this is what that tilt curve looks like. And here's my 0.5 nanometer. I plotted this on a log scale. Really, there's a factor of 21 between those two. So the takeaway is that it's very easy to build really repeatable systems, but that's not necessarily the right criteria. Use the accuracy. You have to actually measure against something known. And it's a little hard to come up with things that are known down at this 0.01 micron, but things like tilt and focus, and those are things that you can vary in a systematic way. Okay, so let me turn a little bit to some of the applications, and good, I've left a good amount of time, I think. Yeah. The first instrument that, and some of you may be familiar with this, is just a sort of a generic sensor. We just put in a camera, put the lenslet array, we fix it very rigidly with a metal mount in front. This is a typical kind of visible sensor. We've made infrared sensors, we've made UV sensors, a wide variety of these things. And basically, at this point, I sort of mix and match lenslet arrays. By now, I've designed 48 different lenslet arrays. And you get a new camera, and you can decide against your list of your catalog of lenslet arrays which one is the appropriate one. But this is a sort of a typical one, lambda over 100 to lambda over 500, absolute accuracy as defined by those measurements that I was showing you a minute ago. And this one, with that particular setting, is probably about 100 waves of total dynamic range that you can get out of it. There's a couple of useful things here. One, and I think I'll show you a couple of them. It's useful for measuring beam quality. It's really useful for optical setups. There's some tools there that allow you to show you the average tip and tilt and the average beam position in real time. And there's a nice display of that you can use. And so that turns out to be a really handy thing to use to dial in optical systems. Now you can dial it in with that tilt as well. And then you can also collimate it as well, because you can measure the overall collimation of that. So I don't know, this is just a couple of things. I mean, here's a laser beam analysis where we're calculating things like M squared, waist size, waist position, overall beam quality. If you're used to interferometry, I can calculate fringes from the wavefront. It's kind of the other way around from it. So, the thing also to keep in mind is that at the same resolution of the lenslet, I can also count up the total amount of light underneath each lenslet. So that total light really is the irradiance of the intensity distribution as well, and it's at the same resolution. So I get an irradiance distribution and I get a phase distribution that I can measure. So from that I can now do numerical calculations. I've got really the full field of this that I can write. It's not really the vector field, but it's the full intensity and phase, the complex field. And I can do a propagation to another plane. So there's, into this same program, we built in a propagator to allow you to propagate it to different planes. And you can calculate your beam quality, or you can actually look at what the beam shape would be some 2 or 3 meters downstream, if that's useful to you. So there are a few assumptions that the phase is constant over the time you're making the measurement, and that it's piecewise planar. And so there's some pieces, if you have partially coherent sources, you may be missing when you're trying to do a beam quality calculation. But it turns out you can actually infer those from the change in the spot size. But the nice thing about this is it comes from a single measurement. It's very often common for people trying to measure a beam quality or an M squared by making a measurement of a laser beam at multiple different planes. And of course, you're assuming that the laser is constant across during that time you're making that measurement. Whereas here, this may be 1 millisecond is all you have to assume that it's constant, because you're going to post-process that. And the way I found to make the best calculation, see if it's in here. Yeah, here it is. So, I mean, these beam parameters, the M squared is really, I'm looking at this far field divergence angle, and I've got a certain spot size, and I've got a position for where that waist occurred. And where is it? Yeah. The way I do that is I use a numeric propagator, and I'll make a measurement of that beam at some place. It doesn't really matter where. And then I numerically calculate what that beam looks like at many other planes, just numerically. And then I'll have some curve of the spot size that looks like this. And then I'll put that into the equations for the beam propagation. And I can determine these parameters like the M squared, the Rayleigh range, the minimum spot size, all those kinds of things. And so it turns out to be a very robust calculation. It is a little sensitive to the camera background thresholds. If you have any background light, then it's really a property of the M squared calculation itself, which is a second moment calculation. It weights a little bit of noise in the corner you're seeing very heavily. So you need to be very careful to get the thresholds right and not have any stray light in there. So, I know this is the, there's in our program we've put a calculation in there to allow you to do this. This isn't instantaneous. It takes about 10 or 12 seconds to calculate this, because we're doing 11 different far field or different intermediate plane Fresnel calculations of that. And so it's a lot of computation that's going on there. Here's a little example. This is actually out at Stanford. We just took a very standard Shack-Hartman sensor and put it at on the eyepiece, essentially, and looked up at a bright star. And we just started off initially looking at the quality of the telescope. And what you see, of course, is atmospheric turbulence. If we just turn on the averaging, average for about 100 frames, then what we saw was this really strong coma term. And it turned out we looked at it a little more closely, and the whole secondary of that telescope was completely misaligned. And so we were able to, in real time, dial that in. We just left the averaging on a boxcar averaging, so we were getting about 20 frames of averaging going on at once. And then just slowly we were able to just dial that in to minimize the coma. And because the whole secondary had been positioned off axis and then tilted to compensate. And so we were able to just bring that right back in. And so we took that telescope from initially being about 3.6 waves peak to valley to about 1/3 of a wave peak to valley afterwards. And so that's just, I put that up there because it was a great example of how if you have a real-time phase available, you can use it to dial in your optical system. And this is a little product that we made just to focus on that whole idea of using the alignment. This is a little alignment screen. Here's the small detector here. It's just for aligning optical systems. And it doesn't have to be a laser beam. It could be just an aperture with light coming through an aperture that you define as your optical system. And what this gives you in real time is an estimate of what that spot looks like. It's centering, and then the little vector is the average tilt. And so, between the XY center and the average tilt, you've got 4 degrees of freedom. And so if you have 2 turning mirrors, you can just steer in something really quickly. So by now, I never do anything in the lab without starting with that information. So because it just makes things very easy. This is another switch gears here to a different application. So this is probably the most challenging application that we've ever built. And this is the idea is to look at the surface, the flatness, and the topography or topology of a silicon wafer. And this effort was actually, we were strongly encouraged to do this by Intel. The next generation of computer chips, almost whenever it is, depends on how well you can prepare that surface in the silicon wafers. And we haven't been doing this now for probably 2 or 3 years, but they were easily at the thousandths of a wave. We're looking at things in the sub-nanometer regime. And there's a number of different ways to look at it. You have the overall, there's a bow and warp, which really doesn't show up on here. That's one feature. There's an overall thickness variation. You can see this wafer is thicker in the middle, actually, than it is at the edges. There's detailed structure of this at a fine level. There's edge effects. And then, as you are actually exposing these with photophotography, they're done in a scanner system. So the wafer is actually moving underneath the lens in a strip. So you don't really actually care about the whole wafer. You just care about the metrology of that little strip. And so it's actually useful to be able to analyze this in terms of what the performance is across each individual strip. And this is all real data off of Shack-Hartman scanning tool that we built. The way you do it is just very simply, you just bounce the light off of the wafer, send it onto a high resolution sensor. This is probably the best sensor that we've ever built. Not a super high resolution, about 0.28 millimeters, and it's just based on the fact that these 300 millimeter wafers, we had some a priori knowledge about what the structure from SEM measurements was, and so we knew to expect it to be in that sort of category. The measurement is made by a scanning and stitching. We just move the wafer actually underneath the sensor, and we overlap little portions of it in the corner, about 10% of each edge. By doing that, what we have is in these overlap regions, we've measured the same surface of the wafer twice, or in some cases, little corners even 4 times. And by comparing those, we can see if there's any stage error or any motion in the machine in between. And in fact, I think the next one shows you these unstitched slopes. This is just the X direction. And you can see there's all kinds of little patchwork of errors here. And so by looking at those overlaps, we can calculate a frame correction. That's this term here. And when we apply that correction, then we can almost completely remove any of those stage errors. The advantage of the Shack-Hartman here is that we measure the slopes, and so we're insensitive to just piston changes, so we're insensitive to height variations, but when we measure the thing that is most likely to be a problem, which is little tip and tilt variations as we move along. And so, so that turns out to be a very good technique. And then when you apply that now in 2 dimensions and put that into a full reconstructor, this is actually a 200 millimeter wafer. If you look at the scale, this is in nanometers. This is plus or minus nanometers I'm showing here. So we're making measurements in the 2, 3, 4 nanometers. And you can clearly see these striations in here. This is a little variation in the boron doping in the silicon wafer itself that has led to a little bit of differential hardening of the surface. So when they polished it, it actually sort of pushed those harder regions down into the material a little bit, and then after the tool pass, they sort of spring back up. And so you end up with, the height of these variations is a few nanometers, 2 to 3. So this particular tool, our spec on the performance is 0.6 nanometers. So I mean, we're down almost at atomic dimensions at this point. So now we had to go to pretty great lengths to do that. The whole tool had to be stabilized to 1,000th of a degree Fahrenheit in order for us to get there. It turns out that was not the hardest problem. The next problem was our optical system had, you can buy temperature controllers to do that. And it turns out when you're down at that level, all it took was a light bulb run by this temperature controller, and we just modulated the current of the light bulb as the inlet to the system. And that was it modulated at some very, very fine level. So, so and
what is the transfer resolution there?
The transfer resolution is, let's see, I'm trying to remember, it's 200 millimeter wafers, and this is 0.28 is the sampling here. So it's about 700 points across, I think, so if I did that in my head right. So the 300 millimeters are about 1 million points on them, so same actual transverse dimension. The other problem we had is that we'd get different measurements on different days, and we discovered that it was sensitive to barometric pressure. Just little changes in the barometric pressure changed the index of refraction between the lenses by just enough that we would actually get a little variation in the focus of it. And so we had to build optical systems that were completely sealed with flat interfaces on the end, and then were all made out of Invar so that they didn't thermally expand. We just enormous lengths that we had to go to. But very challenging problem. Now, it was really a fascinating problem. We ended up with a couple of instruments, and I think we sold 2 of these instruments. So that, from a business point of view, it wasn't a very good business. And the problem was not that this tool was not technologically capable. It was the best tool, still I think today is the best tool on the market to be able to do this. Or the best tool, it's not on the market, but the best tool ever built. The problem is that a small company could not do the kind of support that these giant semiconductor companies needed. And we had one of our tools installed in Taiwan, and going through one of their acceptance tests, which involved running through it robotically loaded wafers 24 hours a day for 10 days straight. And apparently a message box popped up that said, "Would you like to update LabVIEW now?" And it just stopped the whole thing. And that kind of stuff just killed us. It just killed us. So anyway, we eventually actually abandoned this as a business, although all of that technology allowed us to really understand how to build super accurate sensors. And I'll show you an example here in a second of where we were able to apply that. So I don't know, these are just a couple of other examples. This is a ground wafer where they tried to grind that. It wasn't very successful. You see there's a lot of structure in there. It takes a long time to make these wafers, and they'd love to find ways to speed that whole process up. And this was an unsuccessful way of doing that. You see the variation here is sort of plus or minus 25 microns compared to this other measurement that was, plus or minus 2 or 3. So I mean, it didn't make nearly as good a wafer. And you see just sort of a sampling of different wafer structures, all kinds of things. So, well, I didn't know I pushed that button, but it's a good segue to a place where we took all of that, all we'd learned from that, and applied it to another problem. And so, as I think I mentioned to some of you, if you have a toolbox that other people know of, then when people bring you problems, the problems are already tailored for your toolbox. And so the people that fabricate these mirror segments at Tinsley in the Bay Area in California came to us and asked us if we could make a metrology to be able to measure these individual segments in the fabrication process. And as you know, NASA had some problems with the metrology of their first space telescope. And so believe me, they're going to be very careful of this second one. So, and I used to joke that if there's something wrong with this, then it'll be my fault. But it won't be, because there's 100 other people that will have looked at it. So here's the system we built there. It's a scanning and stitching system, very similar to the wafer metrology system. Use the same algorithms. And we just expanded it a little bit. And so this is a 1.5 meter diameter mirror segment on I think it's it's an 8 meter optical table. It's made of granite. And I remember they showed us pictures from when they took it out of the mountain. They blasted it out of the mountain in Vermont. I mean, it was huge, huge optical table. And so there's a point source here that expands up onto this off-axis mirror segment, which should then collimate. So this is tested the way that it's used. So then basically the point source would be at the prime focus of that mirror. And then we take, in this case, we leave the mirror fixed, but we move the whole telescope and imaging system and wavefront sensor. So, and this is on a big motorized gantry that we have in there. So the key thing the other thing that's really unique about this is that they wanted to do this during the early grind phases of the mirror. These mirrors are made of beryllium, and they're first cast and then they're machined. And they wanted us to be able to measure these mirrors right at the machining stage. Problem is that machining stage, while it's very good for machining, still has a roughness of 20 or 30 microns. I mean, it's a rough surface, et cetera. And then they start to grind on it, and they start with a coarse grind, which reduces it to sort of a 10 micron sort of finish. And then what they'd like to do is to be able to take the information out of this with a map and then deterministically polish the high places until they can reduce the overall mirrors structure. Now, they have a process for doing this now with mirrors. And the way they do it is that they work on it and they use profilometry, which is kind of a low resolution measurement. I'll show you some comparisons of it. Very time-consuming metrology. They figure out their map, they do their polishing, they kind of get that as good as they can get it, and then they polish it. They bring it all the way to an optical surface, and then test it. They test it interferometrically. They test it with an optical method. And they discover that, shoot, there's all these low regions. We've got to go back to grinding. Well, what I didn't tell you was it took a month for them to polish it in order to be able to test it. And so that whole process for these mirrors was predicted to take about 3.5 years. It was not a fast process. And so by spending a lot of money on this metrology equipment, the idea was that if we could test it in that ground stage, now we don't have to do anything to prepare it for testing. We just take it out of the grinding tool and put it in this tool, test it, and in one day we can put it back. And so this speeded it up. By the end, the cycle time was 35 days. And by the end of all 18 mirror segments plus one spare finished, it was a 2-year program, which was still included the development of the testing apparatus, but still shorter than if they had just gone ahead and gone right. And unfortunately, we now have 2 of these systems that are sitting there at Tinsley. They're obsolete because they were very custom designed for this purpose, but they might be used again for something else. So the key of that was to build a super long wavelength wavefront sensor. So here is a wavefront sensor designed to operate at about 10 microns wavelength. And this system is based on a silicon lenslet array that we etched, and we put it down in the doer of it's a camera from FLIR. It's called a QUIP quantum well infrared photodetector camera. It operates at 68K, so we had to, the doer is cooled away from nitrogen, and we actually had to pump on the liquid nitrogen to drop it from 77K to the 68K. When you mount something like that, the mounting challenges are fairly difficult. The lenslet array itself, and if I have another, no I don't, another picture of it, has to be mounted in such a way that you can put it in there when it's warm, room temperature, but then it has to be kind of spring-loaded so that as it cools down and everything contracts as you go to this very cold temperature, it doesn't just get loose or fall out or any of those kinds of things. It doesn't get misaligned, those kind of things. And so there's a fair amount of mechanical design, and actually Scott Wilson helped us with this a little bit and some of these kinds of things. And so, and then this is a picture of that. There's the camera with the lenslet array in it. There's a pair of germanium lenses that form the telescope here in front. Here's the lenses here in this. And then, yeah, and here's a picture of one of the mirror segments. And you can see this mirror segment. And it turns out that I think the region that they've actually started grinding on is right here, and then this is just the unmachined, the machined image. Just hasn't been ground on yet. And then you can sort of, you don't see much when you look at this, because you end up with dominated with big astigmatism terms. But once you subtract out, remember I was telling you the difference between that modal and the zonal? So you subtract out that modal, then now you can start to pick up these structures. And this is a print through from the hex pattern of the support structure for the mirror itself. You can see that. The mirror is the face of the mirror is 20 thousandths of an inch thick, so it's a 0.5 millimeter is the face thickness of that. So anyway, and we can clearly see what that pattern is. This is a comparison to the what's called the CMN. It's a coordinate measuring machine, a big Zeiss profilometer. And this measurement took about 36 hours to make, and it's got about 200,000 points. This one we did in 35 minutes. It took us a little longer than that to pump the detector down and get it all cold and those kinds of things. But nevertheless, we can make a much faster measurement. This is about 200,000 points, and this is 1.5 million. So it's a lot higher resolution. So, and then I think this is a final comparison of those. So, and like I say, these mirrors are now all finished. That instrument was designed to have very large dynamic range, but its best accuracy was about a half or quarter micron in that case. And so all those mirrors now are down in the 60th of a wave. And so this isn't a useful instrument to that anymore. So, although we could probably upgrade it with a visible one if they wanted us to. So, and I believe NASA is doing a full-up test where they're assembling the entire satellite in a giant vacuum chamber in Houston, where they're going to do a 100% test of this, because they're not going to have at least that particular problem again. So.
Is that a new chamber? Because when they were designing Kepler, there were a lot of designs.
It's the one they used in Houston to qualify the lunar rover, and it's the old one from the manned space from Apollo. So yeah, and I'm not sure they've probably made some progress, because it's been a few years since we finished that in 2007, early 2007. So they're probably about to do that test if they haven't got there already. Okay, so this is sort of my last application I think I was going to show you, which is to measure the eye. And this is what I am mostly working on right here. And while those other applications, some cases, have a pretty big impact. Potentially, there's nothing like being able to fix people's vision to really say that you're having an impact on the quality of people's life. And the eye is actually an amazingly designed optical system. What we're interested primarily in measuring initially is just the optical errors through the eye, so that we can put some kind of correction on there, the optimum correction of whatever that is. And so, of course, the eye's got a thin cornea. It's got an interior chamber which has an iris in it, and then the lens here, which is actually a gradient index lens. And then, of course, the retina back behind it. So what we did in order to measure the eye was we inject a small spot through a small beam to create a small spot then, on the retina. And there's a fixation target that you look at so that you line your eye up itself to the correct optical path. So you're looking the right direction, because we've imaged some fixation target at infinity. And so this is really like an astronomy guide star experiment. Really, we're projecting a guide star up in there. And then, so our outcoming light is collected by the lens and the cornea. And if everything was perfect, that would be a perfect plane wave. But of course, we have some variation, and that's what we're trying to measure. So, and I guess I was talking earlier about metrology systems. That for the eye, I don't really have to have that accurate a system. The eye's got lots of aberrations. So I don't really need it to be lambda over 100 in this case. Lambda over 10 is really quite good for the eye. So here's the instrument that we built to do that. It's got about 210 micron focal spots. Here's an image from the eye. And the thing that's interesting about this is that it's the same one focal spot, but when we divvy this up with lenslets across this aperture, we're really looking at the same focal spot with all the different lenslet arrays. So any variations, if this is a crummy spot or it's not round or it's some funny shape, it's really only the relative shift between them that matters to us. And since it's the same one that we're looking at with a bunch of really high quality optics, really, then any imperfections in that don't matter, including this injected beam. If this injected beam is a little bit funny shaped or it's distorted by the optics of the eye in the center here, then that really isn't going to matter to us at all. It would just result in a tilt bias, which we're going to essentially subtract out. So there are other techniques where they project patterns onto the back of the eye. And now you depend on the injected beam also being good. And so there's an inherent advantage to this kind of scheme. And this isn't necessarily this is the guide scar approach as opposed to necessarily Shack-Hartman. So, and so these are sort of things that you can do with this. here's your focal spots. Of course, you can compute the wavefront from that. We very typically will present that in terms of Zernike polynomials, although we will also show the zonal maps as well. It's sometimes useful to have an eye image so that you can do a correlation of some sort, and you can register that eye image to the wavefront map. And so the wavefront's just over the pupil. But now I can take that information and put it on another machine and register that to that same eye. And that other machine might be the laser that does LASIK. And so that's actually, in fact, one of the most common applications. Another thing you can do is you can allow the doctor to see through the patient's eyes, because if I have the full intensity and phase of this pupil function that I'm seeing through, I can predict what an image would look like. And so, and I didn't pick a very good pair. This person actually has pretty good vision in both cases. But generally, this is a little bit distorted here in this case. Sometimes a patient, especially post-LASIK or post-trauma of some sort, will come in and says, hey, I'm seeing these streaks that go off in this direction. He tries to explain this to the doctor, and the doctor's trying to infer through some sort of inverse process in his head what's happening. And this allows us to say, that measured wavefront would lead to that phenomena. Or maybe it wouldn't. Maybe it's something that's deeper in the eye that it can. But either way, that information is useful to the eye doctor. So you can also measure the dynamics. And so this is about 10 seconds of measuring somebody's eye. And you can see that there's actually a pretty regular change, in this case of the horizontal coma, which was kind of surprising that it would be in that direction. And we found actually in some cases that we can actually see the heartbeat in this. We can if you plot a time response, you can literally see the heartbeat to it. So so there's interesting things that we're learning use the dynamics. One of the things we're studying recently, I don't know if I had a slide in here or not now, is we're measuring accommodation. We're measuring how people go from focusing in infinity to focusing something very near. And as you get a little bit older, then the lens in the eye starts to harden a little bit and isn't as responsive, and so that is reduced in magnitude is how much you get. There's a whole bunch of schemes that people are putting in place to try to correct for that. But using this dynamic nature is really important thing for that. Another thing you can do, if you can measure the aberrations, you can start to build things to fix them. And so this is an example of using a custom contact lens manufacturing. Contact lenses are already made on diamond turn lathes, and because they want to put a toric in, they want to put just the astigmatism into them. So if I can program it for astigmatism, I can program for coma or spherical aberration, or really anything. I just have to have the information, have to have the registration information out. It sits on the eye as well, which you can also get from those eye images. Once you make those, you need to be able to characterize the contact lenses themselves. And so that actually, we use the Shack-Hartman to do that too. And you need about the same resolution to measure the contact as you do to measure the eye. So it's about the right tool for each one of those things. And then of course you can put it back on the patient's eye and see how well it worked. So I mean, being able to measure this. So this is sort of Shack-Hartman's all the way through that whole process. So, and by the way, this has been done. It's been done experimentally. It hasn't been done successfully commercially yet. I had a picture of a diamond turning machine, but it's not here. It's just, this is actually, we built a special instrument for one of the contact lens manufacturers to measure the molds used to do this at one point. So I was sort of showing the metrology pieces in this line. So, but yeah, diamond turn, it's actually very common to do diamond turning. So, and the most recent work that we're doing, so I guess I'm a little bit over. I know, is it okay for me to go a little bit over? Or, okay, sorry, I wasn't watching the time. This is the most recent thing that I'm doing, is to combine one of these eye measuring instruments with an instrument that also measures the shape of the outer surface, the cornea. So when we do, I guess I don't have one in there. When we do a correction, of course, we generally apply it on the outer surface with LASIK. Even the contact lens is really the outer surface is where that all rests. But what we see through is the total optical. So it's important to measure both. We need to know what both of those pieces are. And so we developed a system that with an aberrometer, very similar to the one I just described, a little higher resolution, a little larger field of view. But it also has what's called a corneal topographer in it. And so this is actually much more similar to a classic Hartman test. There's a pattern in a cone that sits in front of the patient's eye that's just back illuminated. These are just a bunch of little holes. And that reflects off of the cornea from each one of those little spots into a camera, and that's imaged behind a lens here. Let's see if I have a better picture of it. So here's an image from this. The whole idea of a corneal topographer is not a new idea. There's been a thing called a placido topographer, which projected a pattern of rings onto the eye. It's been around a long time. The problem with rings is, while as you know the radial, how these rings shift radially, you don't know where the light actually originated from along the ring. So you don't actually have a measurement of the full gradient of that. You just have a measure of a partial gradient. So whereas from this, we know that spot came from this point on the cone and went off the eye. We can do a direct ray tracing. So you just do a ray tracing solution to this, and you can figure out what that surface is. In the instrument, it naturally gets a little more complicated. There's the cone to project it. There's a lens that we have to look through. You have to illuminate the eye with some kind of LEDs so that you can see to line it up. You've got to have your wavefront sensor path that goes in there. They have to have a fixation target to look at so that they've got something to look at and keep their eyes lined up. And then, of course, you have to capture your topography images as well. So those are kind of all, pieces that all, and there's something like 10 or 11 optics here in a space of 3 inches. And so it also becomes a challenging packaging problem as well. So what you find is that when you compare the elevation of the topography to the elevation, to the total higher order aberrations that you get through the total optical path, in many cases, very similar. And I realize that these aren't quite the same area. This is actually a larger area than this one. So this circle is kind of in here somewhere. And from here you can sort of see pretty similar sorts of features. But you also find cases where they're just completely different. And this is actually a really interesting thing that we found is that in some of the aberrations are actually highly correlated in the internal structure versus the surface aberration, whereas other ones are uncorrelated. And I think I've got a little bit of data in here. This is actually a couple little better images off of the eye. You can see a little clearer image of the kind of resolution. They have pretty similar resolution between the two. So, do I need to stop? So, yeah. Okay. Well, anyway, I'll just explain. So this is the total RMS aberrations, and if it came just from the cornea, then it would be along this line here. And just the point here is that it's well below the cornea. And all that really means is a lot of the aberrations in the eye don't just come from the outer surface. They come from deep inside the eye. And so, anyway, I think I'll skip through all the rest of that. But so I hope I've given you an overview of what the Shack-Hartman sensor is about, and some applications, and certainly willing to entertain questions at this point too.
Have a question? No questions? No. Darren.
One of the things you showed was the setup for doing the metrology of the James Webb Space Telescopes. You talk about starting with a very rough surface.
Right.
So do you get a lot of loss that way and have to compensate in some way for that? Because of the rough surface, you don't get as much specular reflection as you'd like. You have to use really bright sources or something?
Well, yeah, we did use I think it was a 10-watt CO2 laser to do that with.
Okay.
So yeah, it was. We used a pretty bright source. Yeah. So, yeah. We couldn't use a pinhole. We went through a diamond wire die, and that was the pinhole that we used to. So. Yeah. So yeah, you get some loss. Yeah. So, but in metrology, typically just kind of. Actually, we started out with a 4 or 5 watt one, and we actually upgraded it because we needed a little more power. So, yeah.
When estimating the position of a spot, it makes sense if it's a nice Gaussian beam and it proves a nice unbiased estimator. But if that spot picks up a little bit of coma as it goes off axis, how do you know you're not producing a biased estimator?
Okay, so that comes down to we're taking our problem and scaling it down to very small lenslets. These lenslets are typically 100 microns in diameter. So we're taking a very small piece of that. Now, so what that means is that over that little region, it's very much a planar wavefront that we have over the full dynamic range. We're only talking about measuring 20 milliradians or something, so it's not a very large range. And the other thing that we've done is you can actually calibrate it, and I've done this and gone out to the edges and tried to see if there was any variation in it. Really small. It's just really small. And it's mostly just because I'm picking such a small lenslet. I'm really going over a very small angle. If you went to large angles, you would have that problem, probably. But
You're estimating the spot to like 100 kilopixels.
yeah, yeah. But that turns out to be just fine clear to the edges of the dynamic range. Before I have trouble with that, the spots start running into each other or they're outside of the range I'm looking for. So it's just, it turns out to be that's where it scales. So our lenses are also designed to be on the CCD side of the camera. And since they're just designing a computer, we picked the optimal design for that lenslet. So it's not a simple curvature. It's you have to have a square root to describe it even. I mean, it's yeah, it's aplanatic. Yeah. So it's the optimal surface for that shape, to create that. So, but they're usually very slow. So it's not very different from a plano convex lens. I mean, these things are like f/28 or something like that. They're generally pretty slow. So.
Dr. Neal will be in Boulder until